Swayam Prabha. Digital India. Educated India.
Hello all, welcome back. In the previous lecture, we were discussing about streamflow measurement. This lecture is the continuation of the previous one. We have seen the streamflow measurement, direct measurement of streamflow is expensive and also time consuming. We found that streamflow measurement can be done or streamflow calculation can be done by knowing the water level at different locations in the stream. So, the water level measurement we have seen in the previous lecture by using the manual methods and also automatic method. After that, we have seen the measurement of velocity by means of current meter. If water depth is known to us and the width of the stream is also measured, then we can get the area of the cross section, and the velocity which is measured by means of current meter or by any other means can be utilized for the computation of average velocity. When we talk about average velocity, we have seen two ways to express average velocity. The average velocity in the case of shallow rivers can be considered as the velocity at a depth of 0.6 times the water depth, or in the case of deeper rivers, it is considered as the average velocity is calculated by taking the average of the velocities at depth 0.2 times the water depth and the 0.8 times the water depth. So, that way we can compute the average velocity. Now, let us move on to the streamflow measurement. Stream discharge is computed using continuity equation. As I have explained in the previous lecture, once we know the area of cross section and the average velocity, we can easily compute stream discharge or stream flow by making use of the continuity equation. We are very well aware of the continuity equation. For that, we need to have the cross sectional area of the flow within the river and average velocity. So, if both these values are known to us, we can calculate the stream discharge by using the continuity equation. Q is equal to V multiplied by A. Q is the stream discharge, V is the average velocity and A is the cross sectional area of the flow within the river. So, this particular formula or the continuity equation will be utilized for the calculation of stream flow. So, for that we need to have the average velocity value and also the cross sectional area. How can we get the cross sectional area? We are measuring the stage or water level at different locations across the cross section. Corresponding to that, we will be measuring the width of the river, and width and depth is known to us. We can calculate the cross sectional area, and velocity is measured by making use of the cross sectional area and velocity of flow. We can calculate the stream discharge. When we talk about stream flow measurement, there are two ways. One is direct measurement of stream flow, second one is the indirect measurement of stream flow. Direct measurement of stream flow includes different techniques: area velocity method, moving boat method, dilution technique, ultrasonic method. So, some other techniques are also there, but I am discussing here these four techniques. And when we talk about indirect method, those include flow measuring structures. In the rivers at different locations, we will be having different hydraulic structures. So, hydraulic structures such as weir, flumes and gated structure can be considered as the control section, and we can measure the discharge by making use of the measurements at these control sections. So, indirect method of measuring stream discharge is by means of flow measuring structures which are present in the river. For flow measuring structures, the discharge Q is considered as the function of water surface elevation Y. Water surface elevation is measured with respect to an arbitrary datum. So, that depth Y is measured and Q is considered as the function of this water surface elevation. So, for different hydraulic structure, different relationships will be there between Q and depth of flow. So, Q is considered as a function of Y. So, by making use of the corresponding mathematical representation of the relationship between the water depth and the discharge corresponding to a particular hydraulic structure, we can calculate the stream flow. So, that is coming under indirect methods. I am not going deep into the hydraulic structure and computation of stream flow, because this you might have already studied in open channel hydraulics. Second method coming under indirect method of stream flow measurement is slope area method. In slope area method, it is based on the law of conservation of energy, and we can make use of uniform flow equations such as Manning's equation. If it is a flume, we can make use of the Manning's equation to calculate the discharge. Water surface elevation will be measured and the cross sectional area at the corresponding structure will be known to us, and making use of the slope area method, we can calculate the discharge corresponding to particular stream. It is more related to hydraulics. I am not covering the detailed topics related to this indirect measurement, that is flow measuring structures and slope area method. We will move on to the direct method of stream flow measurement. First, we will start with the area velocity method. This area velocity method is also known as current meter method. We have seen two types of current meters, horizontal axis current meter and the vertical axis current meter. By making use of current meter, how the velocity can be measured, we have seen in the previous lecture. So, velocity measurement is ready with us. Now, we need to have an idea about the area computation. So, in this method, we will see how to calculate the area, and once area and velocity is available to us, we can calculate the stream flow. That is why this area velocity method is also known as current meter method. So, measuring the area of cross section of the river at the gauging site is required. So, in the case of measurement of area also, we are not going to directly measure the area. Water levels or stage at different location across the cross section will be measured, and corresponding width also will be measured. So, based on that, we need to calculate the area of cross section, and measuring velocity through each cross section will be done by using current meter. Coming to site selection criteria, the cross section should be well defined and should not change from season to season. The site should be selected in such a way that the cross section of the stream where we are measuring the stages and also velocity, that cross section should be stable. It should not change from season to season. During monsoon season, sometimes some river cross sections will be changing. But in the case of matured rivers, it will be attained a stable cross section. In other cases also, the cross section should be selected in such a way that there is not much changes taking place in the cross section as season changes. And it should be selected on a straight stable ridge, and site should be easily accessible and should be free from backwater effects, because if backwater effects are there, it will be affecting the velocity measurement. That is why it should be free from backwater effects. It should be in a straight stable ridge, and the cross section should not be changing from season to season, and also the site should be accessible. Now, let us have a look into the cross section of the stream. Schematically, it can be represented like this. Non-prismatic shape we are considering. It is not a prismatic channel like rectangular cross section or trapezoidal cross section. So, this is a non-prismatic stream, natural stream. So, the cross section can be schematized like this, and what we are going to do, we are going to divide the width into n subwidths. The entire width of the stream is divided into n parts, and the subdivision is marked by dotted red line. This way we can divide the entire width of the river. There is certain criteria to be followed while dividing the width, that is the width of each subsection or the subwidth should not be greater than 1/15 to 1/20 of the stream width. Total width is there, each subwidth should not be more than 1/15 to 1/20th of the total width. It should be less than that. Second criteria is that discharge in each subdivision should be less than 10% of total discharge. This will come with experience only. When we see a river cross section, we cannot easily understand 10% of discharge will be coming within this subwidth. So, this comes with experience only, but the width of the cross section can be divided in such a way that it should be lesser than 1/15 to 1/20th of the total width of the stream. And one more condition is that the difference in velocity in adjacent subdivisions should not exceed 20%. So, we are dividing the cross section of the stream or river in such a way that the subwidth should be less than 1/15 to 1/20th of the total width, and the discharge through each subwidth corresponding to that area through that should be less than 10% of the total discharge, and also the difference between the velocity between two nearby subsections should not be greater than 20%. So, these conditions should be taken into account while dividing the width of the river. Now, the discharge calculation is done by method of midsection. So, each width is again divided into at the midpoint. The method which we are using for the computation of discharge is based on method of midsection. That is why we need to divide each width into at the midpoint. So, that way the cross section is divided into n-1 segments. The entire cross section is divided into n-1 segments. So, we can look into the figure. So, this way we are dividing each subwidth. It is named in such a way that it starts from 1, 2, 3 and it goes to ith segment, and it will be coming up to n-1 because the total width is divided into n small segments. And at each midsection the depth is measured, stage measurement is carried out at each midsection. So, those are marked by y1, y2, y3, yi-2. This way it will go up to yn-1. Last midsection is coming as n-1 section, that will be the depth at that particular section will be yn-1, and corresponding to the width it is divided into n sections. Total width is divided into n subwidths. So, now we will move on to the discharge calculation by method of midsection. So, here when you look at the subsection, except the first and last, each subsection can be considered as a approximated to a rectangle. So, area can be considered by means of multiplying the depth and the width. So, that way we can get the area. The velocity corresponding to each segment is measured, and you can calculate the discharge in each segment by multiplying velocity and the area. area can be calculated by considering it as a rectangle. But when talking about the first segment and the last segment, it is not like a rectangle. So, the area should be calculated by considering it as a triangle. Total discharge can be calculated as sigma I is equal to 1 to n minus 1 small qi. Small qi is representing the discharge through each segment. Qi is the discharge in the ith segment, and Qi can be calculated by Ai Vi. Ai is the area of the ith segment and Vi is the velocity measured within the ith segment. I varies from 2 to n minus 2. Why it is from 2 to n minus 2? First segment and the last n minus 1 segment are in triangular shape, and other segments can be considered as rectangle, and the area can be calculated by using the formula for area of rectangle. So, Qi is given by Ai Vi. Ai is the area of the ith segment, and Ai can be schematized like this. So, you can see here we are having the area marked by this hatched diagram. So, this is approximately looking like a rectangle. Vi is the average velocity at the ith segment, and area can be calculated as depth at the ith vertical multiplied by half of the width to the left plus width to the right. Since this is a method of midsection, width how we are taking, our section is there, half to the left and half to the right we are taking, and here you can see towards this side and towards this side, half width you are considering, and area is calculated multiplied by the depth. So, that is what is written over here. Ai is depth corresponding to the ith vertical, that is Yi, multiplied by width is taken both towards the half width towards the left and half width towards the right. So, that way we will get the total width, and also depth is already measured, that is the stage which is measured. It will give us the area of the ith segment. Now, Ai can be written as Yi multiplied by Wi plus 1 divided by 2. Here it is Wi and the other one is Wi plus 1. So, half if we consider towards the left and right. So, half of Wi plus 1 will be coming as the width multiplied by Yi. Yi is the depth of the ith segment. So, this is applicable to the segments with I varying from 2 to n minus 2. Now, we have to look at the segment I is equal to 1 and I is equal to n minus 1. That is the segment areas corresponding to I is equal to 1 and I is equal to n minus 1 we need to see, those are in triangular shapes. Now, for the first segment, that is I is equal to 1 and I is equal to n minus 1, it cannot be considered as a rectangular area. Those are in approximate triangular shapes. So, how can we get the area corresponding to these two segments? So, when we talk about this first segment I is equal to 1, the area which we need to have is given by this hatched area. And when you look at this figure, you are having depth at the section 1, that is Y1. But when we are talking about the area, we need to have the depth at this point, that is at width W1 plus W2 by 2, that depth of water, that stage is required to be calculated, but that measurement is not there with us. So, what we are going to do? We are going to compute the depth at that particular midsection by making use of the similar triangle principles. So, we are going to name different points A, B, C, D. So, that way we need to get the value corresponding to CD, that is marked as X. Now, consider triangle AB1 and triangle ACD, that is triangle AB1 and ACD. These two triangles, triangle AB1 and ACD, can be considered as similar triangles, and based on the known values of width and depth, we can compute the depth at the midsection corresponding to segment 1. So, we can write y1 by x is equal to w1 divided by w1 plus w2 by 2. That is y1 divided by x is equal to AB divided by AC. What is AB? W1 divided by W1 plus this much part BC will be equal to W2 by 2. That is what is written over here. Y1 divided by x is equal to W1 divided by W1 plus W2 by 2. From this we can get the value of x as y1 divided by W1 multiplied by W1 plus W2 by 2. So, the base of the triangle is calculated now. We have already measured the stage y1, w1 and w2 are also known to us. So, based on that you can get the value of x. So, once x is known to us, area of the first segment can be calculated as area of the triangle. A1 is equal to half base into altitude. Base is nothing but our x, that is y1 by w1 multiplied by w1 plus w2 by 2, and altitude is w1 plus w2 by 2. Altitude is the width corresponding to that segment, that is w1 plus w2 by 2. Now, area can be calculated as area is equal to half y1 by w1 multiplied by w1 plus w2 by 2 all square. So, this is the formula which needs to be used for computing the area for the first section. In the similar way, we can calculate the area for the last segment also. So, this area expression can be simplified by substituting W1 plus W2 by 2 all square by 2 W1 as W1 bar. So, we can write A1 is equal to W1 bar multiplied by Y1. That is just as in the case of rectangular, how we are calculating the area, depth into width. In the similar way, y1 multiplied by width is not exactly obtained from the figure. We need to calculate. That expression is given by this w1 plus w2 by 2 all square divided by 2 w1. That will be giving you the expression for the width for the triangular section. In the similar way, when I is equal to n minus 1, for the last segment, we can calculate the W width corresponding to that. This is the schematic representation of the last segment. We do not know this dimension because our base of the triangle is this and width is given by height, altitude is given by this. Altitude is not an issue, Wn plus Wn minus 1 by 2. So, this we need to calculate by using the method of similar triangles, written as Wn minus 1 bar is equal to Wn plus Wn minus 1 by 2 all square divided by 2 Wn. And the discharge through these triangular sections can be written as Q1 is equal to V1 Y1 W1 plus W2 by 2 all square divided by 2 W1. Qn minus 1 is written as Vn Yn minus 1 Wn plus Wn minus 1 by 2 all square divided by 2 Wn. So, we got Q1 and Qn minus 1 for I varying from 2 to n minus 2. So, all the segments, discharges through these segments have been calculated given by Q small I, and summation of these discharges will be giving us the total discharge through the entire cross section of the stream. So, this is the method known as the area velocity method. Velocity at different locations, different segments will be measured corresponding to each depth we have marked. We will be measuring the stage and also velocity. Velocity measurement should be done in such a way that if it is a shallow river, the velocity measurement is done at 0.6 times the depth of water level at that particular location. And if it is a deeper river, we need to measure the depth at two sections at 0.2y and also 0.8y, and then we will be calculating the average velocity. So, average velocity is corresponding to each segment is measured, and then we will be calculating the discharge through each segment. Finally, all these discharges will be summed up to get the total discharge through the entire cross section of the stream. Now next is the moving boat method. This is a special type of area velocity method suitable for wide streams. Moving boat method we commonly use in the case of wide streams because for example rivers like Ganga and Brahmaputra, if you are doing the measurement by using the stationary boat, because of the velocity of the flow, the current meter cannot be held in a particular position. So what we will be doing in the streams which are having heavy currents, we will be making use of the moving boat method because it is difficult to maintain the boat in stationary position. That is why moving boat method is preferred in such rivers for the measurement of velocity. So let this be the river flow is taking place in this direction and the boat moves from one bank to the other bank. Boat is moving in this direction. The velocity of boat is given by Vb and the velocity of the stream is given by Vf. Stream is marked as Vf because velocity of flow. Velocity of boat is Vb and velocity of stream is Vf. Velocity is measured by using a current meter which is stored to a boat. So the current meter is held in such a way that it is free to move about the vertical axis. So definitely the boat is moving with a velocity across the river Vb and also the flow is along the river, flow velocity is represented by Vf. So the current meter will be held in a position resultant to the velocity of Vb and Vf. The current meter will be aligning in the direction of the resultant velocity Vr. It is free to move about the vertical axis. The boat is moving with a velocity Vb and the flow is with a velocity Vf. So definitely the current meter will be held in the direction of the resultant velocity. Resultant velocity is represented by the notation Vr. This is the direction of resultant velocity and the current meter will be measuring Vr. The angle between the direction of boat and the resultant velocity is marked by theta. So we can write the velocity of boat Vb is equal to Vr cos theta and velocity of flow Vf is equal to Vr sin theta. And whenever we are measuring the velocity, along with that we will be measuring the stage also because we need to get the stage in order to compute the area, cross sectional area of the river. So the stage measurements are done at different locations, corresponding to that velocity also measured. The stage at different sections will be yi minus 1 yi, that way it will be marked and we will be measuring that. Now if the time of transit between two verticals, the time taken is Ti, then the width between these two sections can be calculated by Wi is equal to Vb Ti. Vb is the velocity of the boat that we can calculate from the velocity measured by the current meter. And the time taken to travel this much of distance is noted. So the width can be calculated by using the formula Vb Ti, velocity multiplied by the time. The average flow velocity in the vertical Ib Vf, that is Vf we can calculate from the velocity measured by the current meter Vr with us, and the depths at two verticals I and I plus 1 are yi and yi plus 1. So by knowing the depth and the velocity and also knowing the width, we can calculate the flow through each segment. So we can get the flow in the subarea between I and I plus 1 verticals as Qi is equal to yi plus 1 by 2 multiplied by Wi plus 1 into Vf. That is, here we are considering each subareas are rectangular subareas, and at the end points it may have to be considered as triangular. So we may have to calculate the dimensions accordingly. So Qi can be calculated by making use of this formula, yi plus vi plus 1 divided by 2 multiplied by Wi plus 1 Vf. Here we are going to substitute for W and Vf because we know the formula. VBTI, that is width between two sections, can be calculated by knowing the velocity and also time taken for that much of distance to be covered. So, VBTI multiplied by VF, and we know VB and VF. VB is given by VR cos theta and VF is given by VR sin theta. That we will substitute over here, yi plus 1 by 2 VR square cos theta sin theta Ti. This is the expression for discharge through that particular sub area. I will be varying from 2 to n minus 2 and initial and ending section, that is initial triangle and at the end of the cross section. Those two segments are triangular in shape. Those areas can be calculated by means of the formula for triangle. So, we can get the total discharge through the cross section by using the summation of Qi. So, total discharge Q is given by sigma Qi. Now, let us see the third technique, that is the dilution technique for measurement of stream flow. In this case, a tracer is injected into the stream at a constant rate Q meter cube per second, and the tracer is having a concentration of C1. So, this tracer can be sodium dichromate or a radioactive chemical. So, this is injected into the stream with a concentration C1 at a constant rate of Q. Sometimes at a constant rate of Q also injected, or together all the element, all the tracer will be together, it will be injected. It depends on the study in which we are carrying out. Let Q be the discharge in the stream which is having an initial concentration of tracer C0. Stream discharge is Q, and also we are assuming that there is small amount of tracer present in the stream. That concentration is given by C0, and the tracer is chosen in such a way that the tracer will be mixing completely with the flow. The concentration of the tracer will be measured at a downstream point where the concentration becomes a constant value C2. So, in this method what we are doing, we are injecting the tracer at an upstream point and the concentration of the tracer is C1, and already the water is having certain concentration of the same tracer as C0. Tracer is allowed to completely mix with water, and we will be measuring the concentration of tracer at the downstream point. So, that is represented by a constant value C2. And at the steady state, we will be making use of the continuity equation for the tracer, and the continuity equation can be written as QC1, that is Q multiplied by C1, that is the amount of the tracer added. The rate at which the tracer is added is small q and the concentration was C1. So, QC1 plus, and already in the stream some tracer is there with a concentration of C0 and the discharge is capital Q. So, QC1 plus QC0 can be written as equal to Q plus QC2. This is the concentration at the downstream sample station, and the rate will be written as Q plus Q. This equation is rearranged like this, and we can write Q as small q multiplied by C1 minus C2 divided by C2 minus C0. So, here in this case, if C0, that is the concentration of the tracer which is present in the water, is of very small quantity, we can neglect it. So, the equation can be rewritten as Q is equal to small q multiplied by C1 minus C2 by C2. It can be rewritten again as Q multiplied by C1 by C2 minus 1. So, initial concentration of the tracer C0 is very small quantity that we are neglecting. The stream discharge can be calculated by using this formula. So, we know the rate at which the tracer is added and the concentration of the tracer is known to us, and C2 is the concentration at the downstream end where the sample collection is done. So, based on these values we can calculate the stream discharge. Now, next method is the ultrasonic method. In this what we are doing, flow velocity is measured using ultrasonic signals. This is less time consuming and this is very commonly used also. In this we are making use of the ultrasonic signals. How it is done, let us see. This is the river section we are considering and the flow is taking place along the river and the cross section of the stream is marked like this. It may not be always rectangular, it will be having irregular cross section also. In such cases, we have to provide a regular cross section for the measurement convenience. Water level is up to a depth of small d in the river and the base width of the river is small b. And the velocity of the flow is represented by v and c be the velocity of sound in water. Because it is based on the ultrasonic signals, so we are assuming the velocity of sound in water as small c and velocity of flow is represented by v. Now, what we are going to do, we are installing two transducers A and B on either side of the stream. On either side of the stream, we will be installing two transducers A and B like this, and these are installed in such a way that the line joining them makes an angle of 45 degrees with the horizontal. The length between these two transducers is capital L and it is making an angle of theta, or it can be 45 degrees with the horizontal. It is provided, installed at a depth of h, at a water depth of h on both the sides of the stream. So, A and B are the transducers, it is installed at a depth of h from the bed. Now, A sends an ultrasonic signal which is received at B after a travel time of t1. When A is sending a signal, it is received by the transducer at B. The time taken for the signal to travel up to B is marked by t1 and at the same time B is sending a signal and that is received by the transducer A. So, the time taken for that is represented by t2 and the velocity of the signal along the flow path is marked by Vp. B sends a signal to be received at A after a time of t2. So, A is sending signal and that is received there at B, and when B is sending the signal it is received at A. So, we can write T1 is equal to L divided by distance between the transducers divided by C plus Vp. Why C plus Vp? Because the velocity along the flow path is along the sound, velocity of the sound, and we can write C plus Vp is equal to L by T1. And now as far as T2 is considered, it will be L divided by C minus Vp because opposite to the flow path. So, it is L divided by C minus Vp, C minus Vp is equal to L by T2. Now, what we are going to do, we will subtract the second equation from the first equation. So, we will get 2 Vp is equal to L multiplied by 1 by T1 minus 1 by T2, and Vp can be written as L by 2 multiplied by 1 by T1 minus 1 by T2. But we know Vp is V cos theta. Vp is in this direction and V is along the flow direction. So, Vp is equal to V cos theta. What we want to get the value corresponding to V, that is the velocity of flow. So, V is Vp divided by cos theta. So, V cos theta is L by 2 multiplied by 1 by T1 minus 1 by T2, which gives the velocity of flow as L by 2 cos theta multiplied by 1 by T1 minus 1 by T2. So, velocity of flow can be obtained by using this formula, by using the ultrasonic method. So, V is given by this expression. This velocity is the velocity in the stream at a height of h where the transducers are installed. It is not giving us the average velocity, it is the velocity at a depth of h water depth of H where the transducers are installed. So, we need to install these transducers in such a way that it will give us the average velocity. So, this need to be taken into account. In the ultrasonic method, the velocity which we are obtaining is based on the position of the transducers which are installed within the stream. Now, coming to the advanced flow measuring devices, nowadays we are having so many advanced techniques. Some of them are acoustic Doppler current profiler, which is represented by ADCP, and acoustic Doppler velocity meter, ADV. Both are working on the principle of Doppler effect, that is the difference in frequency which is taking place as it moves away from the source. So, that Doppler effect principle is taken into account, and based on that we will be getting the velocity of flow. I am not going deep into the methodology related to that, but you should be aware of these instruments which are used for measuring velocities nowadays. So, coming to acoustic Doppler current profiler, the advantage in this case is that it is not giving us the point velocity, it is giving us the velocity across the cross section. So, ADCP is mounted onto a boat and guided across the surface of the river to obtain the velocity and depth. We will be getting the water depth and also we will be getting the velocity. The sound is transmitted into water from a transducer to the bottom of the river and receives return signals throughout the entire depth. Entire depth it will be sending the signal, and the change in frequency or the Doppler shift is measured by ADCP, and that will be translated to water velocity, and it uses the acoustics to measure the water depth by measuring the travel time of a pulse of sound to reach the river bottom and back to the ADCP. ADCP on the surface of the water, and it sends a signal to touch the river bottom and it comes back, and based on this it will be calculating the depth of the stream also. So, we will be getting the depth of stream and also we will be getting the velocity. Velocity across the depth of the stream we will be getting. So, the advantages in this case is that it provides a profile of velocity and also direction instead of just point measurements. In the previous case, when we were talking about current meter case, at a particular point where we are intending to measure, we will be getting the velocity at that point. But in this case, we will be getting the velocities across the depth, entire depth we will be getting, and based on that whichever location velocity we need to use or we need to find out the average velocity, we can calculate from this. And it takes less time compared to any other method of discharge measurement. And discharge measurements can be made during flooding condition also. In this case, we do not have to worry about the position of current meter. Whatever be the condition, whether it is the lean period or high flood condition, we can make the measurements and compute the stream flow in a river. So, we do not have to bother about the season. During flooding condition, by making use of other techniques, it is very difficult to get the velocity or stream flow, but by making use of ADCP, we can calculate the stream flow during the high flood conditions also. So, here I am winding up this topic, and the references related to this stream flow measurement are given over here. And today's lecture we have seen different methods of stream flow measurement, direct method and indirect method. In the indirect method, we were making use of the hydraulic structures present over the site, and in the direct method, 4 different methods have been explained in this lecture. And based on that, we have seen stage measurements and velocity measurements will be done in the field, and the area calculation will be done by making use of different principles. Since different strips we are considering, central middle portion we can consider it as rectangular strips, and extreme ends can be considered as triangle, and the corresponding areas and the velocities are known to us. Based on that, by making use of the continuity principle, we can calculate the discharge, and total discharge across the stream can be calculated by using the summation of the individual discharges. So, here I am winding up this lecture. Thank you.